Welcome, everyone, and thank you for your time to come visit us and see our presentation. So today we will be mainly talking about 3DEXCITE, create and show. First, if the button works, yeah. First, some quick agenda points. So first we'll go over who we are, what's the company all about. Then we'll go over some of the challenges that we're all currently facing and showing more about show and create. And then it's time to delve a bit deeper in the technical underbelly of the beast and see what it's all about. And then at the end, there is some room for Q&A. So first of all, who are we? We are 3DEXCITE, and we've been in the business for the past 25 years in the business of product visualization with a heavy focus on the automotive industry. So you can say we can kind of have a long history of creating virtual twins of the vehicles and creating content like brochure images, web configurators, and things like interactive experiences. So you might see at the corner there's not a 3DEXCITE logo, but Dassault Systèmes logo. We didn't steal another company's presentation deck. It's actually in 2014 that our company was acquired by Dassault Systèmes. It's the French software company that you might know from CAD software like CATIA and SolidWorks. But actually, it's bigger than that. It's a science-based company that is all about 3D experiences and virtual twins and delivering software to create virtual twins for a wide range of use cases to develop new innovative products and experiences. Not only in the automotive sector, but also life sciences, industrial things. So it's quite expansive. And since we were acquired, that also impacted us. So we had to change our goal a bit. And we're all about bridging the gap between product design, so the CAD stages, up until creating a commercial virtual twin to the actual content and the marketing world. So next we will show you a short video of what we've always been creating. If the video works. Thank you. So first, a small disclaimer. So it's not obviously not only Unreal that we use, but quite a variety of tools, whichever fits the job. The question is here, so are we scalable enough to do this kind of work in the future for whatever our clients would need in the next few years? Because we live in complex times, both the marketing industry as the OEM, the automotive industry is changing rapidly. So as you've also heard in the previous presentation by Doug, we are changing quite a bit things. So on marketing side, the amount of channels that need content is rapidly increasing. Things like social media requires a lot of different content. So how do we approach that? Also on the industry side, we've heard it before, like electrification, new autonomous driving features, software-defined vehicles, things like that. Yeah, are quite some challenges for all of us. In general, for us as a company, it means that there's a lot more content needed. We need to deliver a lot faster. And unfortunately, the budgets are not linearly scaling. So if you need 10 times the amount of images, we can't bill 10 times the budget. So that's quite a challenge. So we have been thinking long about how to approach it, and we were too young to retire, so we had to find a solution. So that resulted in a render-on-demand solution. So something that we call create and show. And we want to tackle 3 separate things. So one is to have configuration scalability. So we always want to show the right variant of the car for the right market, for the right audience. We always need the car to be product correct and always up to date. So if something changes upstream in the design elements, we want to enable the trickle down effect to go right towards the marketing content as fast as possible. And next, we don't just care about the car, but also we want to offer context scalability. So we want to make sure that the vehicle is also shown in the right circumstances. So it doesn't make much sense to show a car on a snowy landscape when your market is actually a southern country. And next, the most complicated things is we are not working in an isolated mode. So there's a lot of channels that need different content, and it's just not one company doing everything. So there might be an agency that does print campaigns or a TV commercial and the brand website, but there's also external partners like mobile applications like for Uber or Bolt. As an example, I went to the conference here with a Bolt car, and the car showed up. It was a nice Skoda Octavia, green one, nice car. And the picture on the app was a blob with 4 wheels. So that's unfortunately the reality of today that we also try to tackle. And aside from that, we see horrible things nowadays. If you visit like local dealerships, you see things that someone's nephew that's 15 years old has bolted together. And that's unfortunately because OEMs pay millions of dollars on car design and on the creating a visual brand identity. And we may want to make sure that that effort is shown in all communication material that they have. So how does that work? We start from a commercial virtual twin. That's the single source of truth where all the logic, all the information of the car exists. And then we want to branch off into 3 different parts. And for a change, let's start at the bottom. It says the axis, and that's something we won't delve into too much today because we're all about show and create today. Axis is more about exporting configurations of the model for agencies, for mobile devices, things like that, even HMIs. And today we're here for show and create because that's powered by a fantastic 3D tool that maybe some of you heard about, and that's called Unreal Engine, of course. So what is show and create about? It's 2 sides of the same coin. So we have the commercial virtual twin at the center, running in a cloud instance, running Unreal as it's rendered today. And the difference between show and create is actually the way that you generate content from that infrastructure. So let's dive a bit deeper into what create does. Create is all about self-service. So it offers a nice web user interface in which you can log in if you've gained access. And then you have a full user-controlled system where, depending on your access rights, you can go through a template-based guided or Pro Studio setup, where, for example, a market just needs to change a configuration of a car, so they can log into that. In Pro Studio, you can change camera angles and things like that. So in reality, that looks a bit like this. You log in, you select your car, you can start changing any configuration. Also context scalability, so you have a choice over different environments, but also change lighting, so things like daytime changes you can also do. And then, of course, you can generate an image output from that or save it as a template for other people to use. And you have an overview. All the metrics are there. You can create templates to use in the future. So that's all about Apex 3DEXCITE create. Names is sometimes a tricky thing if they change it during the course. So next we have 3DEXCITE show. So that is all about API access. So on the screenshots you see here, you have a makeup URL. So it basically you send a request for an image, it generates it into the cloud, and it brings it back to you underneath 1 second, of course. So you have a URL that requests it, and that contains all the information for the generation of the image. So in reality, for example, if you have a website, you have different images on them. And currently, usually your images are just static disconnected images. But in this case, it's all connected. It's all API calls to the 3DEXCITE show system. And that means that if there's at one point in time a change on the car, we can make it happen that the cloud instance is updated. And then, of course, automatically all your content is updated. You can also do things like if you click on one of the buttons and change the configuration, that also the other images are changed because it just updates the requested image. So it's a quite powerful way. You can generate a lot of content from it. For example, 2D images, you can have turntables, or if you want, show also supports pixel streaming, so you can also have an interactive streaming sessions. And that's not just only for like the big marketing images, but things like the icons you saw for the car paint samples, you can also generate those automatically from the system. And since we're talking about marketing images, we're all about high quality. So we try to push as much as we can within certain technical limits because we only have less than a second to generate one image. And all the images you've seen in the presentation come out of the 3DEXCITE show solution without any processing involved. The great thing about using Unreal, of course, is they push boundaries in a graphical way at a super fast pace. So that enables us to quickly adapt those technologies and keep pushing the quality as far as we can. So how does the process look like? Because the title of the presentation says automation is key, so we try to automate as much as possible. So here we venture into the more nerdy parts of our talk. So hopefully that gives you some ideas to how to implement certain standards and ways to approach things. So a little story first. So we always have the engineering virtual twin as the first source of truth. So that's the actual CAD data, how the car is manufactured, and we have that. And in the end, for our solutions, we need to build a commercial virtual twin. So there is a difference between that, but we always try to keep the link between both. So if something changes on the design side, we want to push that as fast as possible towards an update on the commercial virtual twin. As you might have, as you probably know, the engineering virtual twin misses some information. For example, product variants. They do, well, in the engineering twin, you do have all the information there, but not logically structured or made that you can easily switch things. So that's something we add to the commercial virtual twin. Also, soft parts is a difficult thing because in the engineering world, they don't really care about stitches and folds and things like that. So we also have to add that data as well. And the material information is also a big part because engineering cares about materials, but just the properties, how strong is a material, how much does it weigh, and we care about the visual fidelity and how it looks, of course. So the goal is, in the end, we have a completely complete 150% model with as much data, metadata that we can get from the engineering data. So here we have a nice video, a speeded recording of how we go from DeltaGen, the software that we have to create our commercial virtual twins in, towards Unreal. It's like a 20-minute video, so I will stop here and let us play the video. No, it's only 3 minutes, so I will give you some guidance along. So here we have the model with all the variants and all the configurations. and materials, and then we export through USD. So we try to use standards as much as possible. We have a custom USD exporter that generates not only the USD model, but also auxiliary files. So we also export all the variant data and all the material data as separate files to have a complete set of data that we can use more upstream. Once we have that data, we use a MaterialX system to generate MaterialX files from all the materials. Normally you should see, yeah, here is the MaterialX exchange exporter. So we talk more about MaterialX in the next slide. And then we can jump to Unreal. We start with our own custom template and a fantastic tool that we have, which is largely Blueprint and Python based. And that's the Carl USD importer helper with a very nice interface, of course. So what does that thing do? It hooks into the interchange framework from Epic to import the USD file and the MaterialX files. Sometimes, as you've probably worked with the interchange framework, it not always works as we intended. So we use it for what works, and we bypass things and make our own system where it fails. The nice thing about the Carl importer is also it uses content plugins. So it gets them from Perforce, so we're always using the latest versions. For example, a material library or environments that we have already fixed, or the logic for show and create. So then all the data gets pulled in by USD. We don't use USD stage for real-time purposes because we notice that the performance is not there and we care about every millisecond. So we use it as a transfer format. So we, in the end, just get all the Unreal assets in there. Same with MaterialX, so we get all the materials in there as well. 4 more minutes now. So what we end up with after importing everything is a level. It's a custom new brand level with a car inside, with all the materials into it. It's all switchable, and it also populates a variant manager. We currently don't really use the variant manager for the Epic. Wow, it's hard the naming. The show and create solutions. But it's like an artist-friendly way, so artists, when they are working on the scene, can easily switch configurations to see how they look.
And maybe just before you go to the next topic, so normally, so this is the boring way of showing the even more boring way, because you normally wouldn't look at the screen while you're doing that. So this normally runs headless somewhere within our CI/CD infrastructure, and then you just get a notification when your stuff is ready. You open up Unreal, and then boom, off you go.
Would be very boring to show that, just a black screen with some text for 3 minutes, but
yeah.
So, as I said before, we do use USD and MaterialX, like standards is important to us. We won't cover USD as much because there's lots of information already available, but we will take a look at how we approach MaterialX today. All right. So on the left side, we have our single source of truth, the DeltaGen commercial virtual twin, which contains all the materials. And those materials are already approved by the client. So we don't want to touch those and make sure that they get across to the other side, being Unreal, without too much difference, because we hesitate. Well, we don't want to introduce a secondary approval process, which is an extra burden on the client. So our shader system in DeltaGen is the Enterprise DSPPR. I think it's even open source. Yeah. But it's not mapped to Unreal directly, of course. So what we do is we get all that data that we have and export it, like we've said before, and then we generate a MaterialX file for each material. And that's more of a storage system, so it contains all the parameters that we have access to. We try to build it in a quite modular way, so if at any point something changes, like on DeltaGen side or Unreal side, we just swap out that module. We don't have one big monolithic system that we always need to change and update. So in next phase, we have exporters and converters. That's the tricky bit, because those try to map the values that we originally have from DeltaGen and make sure that that adheres to the OpenPBR shaders. That way we end up with materials all in the OpenPBR space that we can also preview with other tools like USD View or MaterialX Viewer. And we sometimes add extra information to that, so we have more data to work with in Unreal. So those files, so that material library, can then be used together with USD, either in a linked way or an embedded way. Currently, we mostly use it as a linked way. And then you're basically free to go to any software that you want. So in our case, that's Unreal. So we use the Carl importer that you've seen before to ingest all the MaterialX files. And in the end, they are mapped to custom master materials in Unreal with the material instances. So it's like that. So we are based on custom master materials in Unreal, and as we said before, we use OpenPBR as the intermediate open standard format, and use the converters to convert from TSPBR to MaterialX in OpenPBR. So we always try to use as much as possible what there already exists, what technology exists, and even at the point where there's something that doesn't work for us, only then we try to circumvent any process. And as we said before, we want to use the latest state-of-the-art workflows and features. So because we're quite modular, it's for us quite easy to, for example, the master materials in Unreal, to swap them to substrate materials, to then go into substrate support. What's better than having quotes from people from your own company? They are not biased at all. So the nice thing by doing the MaterialX workflow is that the material flow from approved materials to Unreal materials is quite seamless and looks the same. In the past, we had to spend days in updating the materials and making sure that everything looked okay. So we don't have to do that anymore. We can spend more time on actually creating great looking content without touching the materials. And something to mention, we always try to work with the latest and greatest. So this ball you see here is already using nanite tessellation. And that's it for my side now. Timon can go ahead.
Yeah, so you thought this was technical. It get worse. So now that we have this complete virtual twin and it's staged and people start doing all these great 3D environments, there's much in the process that needs to happen. As Kara said before, we're going to do it in less than a second, and you just have to trust us on that. So this is super exciting because normally you wouldn't talk about stuff like that, and I'm hoping you're not getting too bored, but this is the super nerdy part. So whenever we do a 2D image request, there's quite a lot happening. So for instance, we need to make sure that the requested options, like what wheels with what colors, actually come out as a buyable option. So if it's not buyable, we shouldn't produce the image in the end. On top of that, we do stuff like sanitizing input data, checking if we have it cached, if the cache is still valid, and stuff like that. And then at some point, we obviously need to ask Unreal for an image. And these are all pluggable systems on the left-hand side. So for instance, we can hook into outside code validation systems from SAP or whatever is around. But then the number of 1 second changes slightly, by the way, so that's that. So when we do a request, there's quite a lot happening. And one of the key things that you always have to remember is laziness is speed in the end, because if you don't do anything, there's nothing to wait for. So in the single request, we might change the geometry of the environment fully, as well as the car, as well as material shaders and whatnot. So you really need to make sure that you do not redo anything. In general, we're trying to keep the engine when it's in a 2D rendering mode stateless. So it doesn't know anything about anything. It just does as it's told. All the verification happens somewhere else because, again, speed, and we can put it on different other machines. As Kara said, we use the variant manager for ease of use when working directly in the engine. But at runtime, we have a custom implementation that works based off metadata that we ingest into all the geometry and stuff. Yeah, and that all happens in under 1 second, although it looks like it's not. So this is a small test UI that we have for artists, and it lets you simulate the process within the engine or within the editor. Excuse me. So things are changing daily, basically, inside the engine, outside the engine, in the world. So we have to keep a rapid development environment. And the way we do that is we're having a KISS principle. So we're staying in Blueprint as long as humanly possible, and then identify parts that just are not giving the speed that we need, and then we shift them over to the development team. So the actual implementation might be done by a tech artist instead of the development team, and then only if we need the few more milliseconds, we shift it over and find a better solution, or an even better solution. So you have to talk to the engine somehow, and also this is time critical. So we're using protobuf, which is a binary packaged magical thing. So you have definitions of messages, as you can see here on the right-hand side of the screen. So these are not standard Blueprint nodes, but nodes that we automatically generate based off protobuf definitions. And we have a little tool. It's called proto-cgen Unreal. Great. And that takes the protobuf definitions and outputs a full Unreal Engine plugin that you can just pop into the engine, and it works cross-platform. And of course, we need to make sure that we can both, before production and while the production is running, validate data. So you've seen it on the screen before, but this is basically a UI that we have. It's based on Python. It uses the same protobuf definitions, but compiled for Python. And it runs a little message broker, and you can actually put in like full URIs coming from the backend, and it kind of resembles the process to let you visually inspect something in engine. So that's the editor part. And this is what it looks like on the cloud. So on the left-hand side, we have a little visualizer that we made just to showcase all the funny bits and pieces we have. So it can do like 2D creative images, then turntables, as you see in this case, and then also pixel streaming. The turntables are 18 images, I believe. And this is speed up a little bit, but essentially it runs 3 instances of Unreal Engine in the back. And I cannot even tell you how many GPUs, because it might be 1, it might be 2, it might be 3. We don't really care. And the reason is it's highly unlikely that the engine at the very same millisecond tries to output the final image. So we are over provisioning all the GPUs, and we are only constrained by what we can fit into VRAM. So there might be 3 instances running, 2, 1, doesn't really matter. On the right-hand side is the super boring part. So that's logging outside the engine. So this is a shipping build, but still we have a custom plugin to create structured logging that then gets streamed through the systems for monitoring, alerting, inspection, and stuff. And then you have a behemoth of a something that day over day scales up, down, left, right. It doesn't really matter, and you start to not care too much about it. So we're running Kubernetes on the cloud and on bare metal. So on the left-hand side, we just did a manual scaling of some workers, and in a bit you will see new machines popping up that get scheduled automatically through metrics systems that we have in place. And on the right-hand side shows the mess of communication that's happening, and we have some inspection tools to just see how many requests are going from any worker to our message queue or back and forth. The scaling itself, so on the left-hand side, 50 seconds, great. This was a manual scaling, but we do have systems that can scale based on request rate, time of day, minimum instances, maximum instances, pre-warmed instances. It does all of that. So as you might imagine, we put a lot of effort into thinking about how to build such a scalable system and into decoupling things. But you don't really have to decouple all the things. So just hot take, everything is microservice nowadays. Don't do it. Keep it monolithic as long as it works, and then just design it in a way where you can split it up after the fact. So if you start designing a microservice-based architecture from the get-go, it's getting complex quite fast. But we are not stopping there. So we are not only automating all the things, we're also decoupling all the things. So we, as you might have guessed by now, it's not running on Windows. So we're running on a containerized platform on Linux. And we have a runtime container that's basically super fast at rendering black frames. So we're probably the fastest in the industry to render black frames. And then we run that as the base runtime for everything. It's based on Unreal Engine's runtime container. And then at runtime, we dynamically load content in that we package individually. So the car is its own package, and each environment is its own package, as I said. So each and every container gets configured at runtime, so they have like an initial state, and then we can dynamically load data as we need it into the engine. There are a few caveats though, and it's not all gold. So there are a few things, few caveats that we're gonna look, but the pros are just there, right? So with faster deployment times, we don't have to repackage content and validate it if we do a bug fix on any logic or anything. So what doesn't work? Surprisingly, Unreal Engine is a game engine, and game engines tend to care about the beautifulness of all the frames together. And for 2D rendering, we don't. We care about one frame and one frame only. So early on, I asked ChatGPT if there's like a I'm done rendering callback in Unreal. ChatGPT said yes. In fact, it's no. It just keeps going. There's no end to the rendering. As long as it runs, it renders. So you have to come up with creative ways how to determine if a render is done. For instance, if you change geometry quite a bit, in the worst case in each and every request, there's still parts of old geometry maybe affecting reflections and stuff. So what we do is we keep a separate history of all the previous frames, and based on some mathematical craziness, we determine image stability for that very frame. Another thing we found is you quickly start to think about why render everything if you can just put it on a alpha mask. It's possible. That was the transparency mode. But it wasn't to our expectations. For instance, we saw problems when you do semi-transparency, like tinted glass. The alpha mask wasn't enough. So we had a great colleague just over a couple of days write a custom CUDA kernel that we now load into the engine, and we offload the transparency part through even more trickery into a CUDA kernel. Another thing, if you want to build something like we've shown today, make sure that you just stay ahead, and because it's super fastly changing. So if you look at the GitHub repo for Unreal Engine, there's so much happening. So yeah, test early. We always try to be able to build with new versions, and we sometimes do just as testing and evaluation, and we find problems, and then we work around these. Things break. It's software. It's not Microsoft Excel, and even that breaks. So it's not used by as many people. And if you build such a system, there are other parts contributing to the whole thing. So be sure it breaks, and have things in place that help you fix breakages, best case on their own. And then the Linux bit. So Linux works on Vulkan. Vulkan is a great graphics API, but it's not the same as DirectX, and it does not always work the same, and it does not always produce the same result as Windows DirectX. So make sure to provide infrastructure to test. In fact, we run all engine instances on Vulkan, also on Windows, just to make sure that we see problems early. CVARs, I love them. Oh no, it's not yeah, it's CVARs. So we found that you need CVARs, right? If you're at the cutting edge of anything, CVARs help get the milliseconds down, image stability up. But sometimes you start working against the CVARs you introduced last week. So we now remove any CVARs from configs that don't have a reason to be there, just as a pre-process step. So you cannot introduce anything into the engine that nobody knows about. And finally, you should know what's running where and why and where it came from, because system sometimes decides on itself, I'm going to change something. You might not know about it, so keep track of what you have. And to keep track, there's a great thing by Perforce, which is called Perforce, and then Git. So we use both, Perforce mostly for the content part, and then Git for all the code part. And then whenever we release engine plugins from Git to Perforce, they get flagged with commit hash ID, so we exactly know what runs where. And we can also ask the engine at runtime how it's what it's composed of. So you won't see these anymore. I've seen too many of those because there's no manual build process. It's all managed through infrastructure, and everything is linked to everything. So whenever we have something changing, there's a link within the Jira ticket, for instance, and then in the Jira ticket, there's a link back to whatever commit that was. And yeah, no more C:/temp because it doesn't matter. You can work in temp folder if you like, but since we do version control, you have to commit it at a certain point to get it into any project anyway. So lastly, these need tools, right? So on the right-hand side, you were able to see a few internal tools that we have that we use to publish content, build engines, and just keep track of stuff. So this is mostly written in Python, and it can be written by a tech artist. It doesn't really matter, but it has to work. And just as a quick shout out, so we have a great team of engineers, tech artists, and generally people all around the world. And it's crazy what they do. So thank you very much.